Hi everybody, it's Miss G here. I'm going to talk to you in this lesson about single displacement reactions and double displacement reactions. If you take a look at this single displacement reaction, what you're going to notice here is that you've got some element that's all by itself and it's going to be reacting with a compound. Now there's a couple things I want you to notice. First of all, in this single replacement reaction, we've got a metal sitting all by itself. And if it's a metal, it's going to become a positive ion when it reacts. It's not a positive ion right now. It's just a piece of copper metal. If it's a more reactive metal than the metal that's in the compound, in this case it's silver, then the copper is literally going to replace the silver. They're going to switch places, and the silver is going to become an element by itself, and the copper will then combine with the nitrate. But this only happens if the copper is actually a more reactive metal than the silver. To tell if it's more reactive, you have to take out your periodic table and flip it over. You should take a minute to do that now. It's worth it. Okay, once you have your periodic table flipped over, I want you to look for this activity series. It should be in the upper right-hand corner. And it lists the metals in order by reactivity. The elements listed first are very reactive, and the elements that are listed last, like platinum and gold, are not very reactive at all. That's one of the reasons platinum and gold are so great as for jewelry, is because they don't react with a lot of things. Well, you're going to notice here that if we look up copper and we look up silver, you're going to notice that copper is in fact more reactive than silver because it comes first. So copper is able to replace silver. So if we go back to this original slide, you can see that that in fact is going to take place. The copper is going to react with the silver. Right over here on the right hand side, I just have a note about what I just talked about, that activity series. Sometimes the element that's all by itself is not going to be a metal. Sometimes it's going to be a non-metal. So it'll be on the right hand side of that zigzag line on the periodic table. Here's a case in point. I've got chlorine, which is a non-metal. It's going to replace the non-metal in the compound potassium bromide. Chlorine becomes a negative ion when it reacts, so it's going to replace the negative ion in potassium bromide. But again, it only does that if it's a more reactive non-metal. So here's what you have to keep in mind. Non-metals react when the replacing non-metal is higher on the periodic table. So as long as chlorine is higher on the periodic table than bromine, it's more reactive and it's going to replace it. I don't know if you remember that activity that we did when we were studying the periodic table, and we were looking at which halogens were more reactive. The higher up they were on the periodic table, the more reactive they became. So what I want to do is a couple of sample problems for you down below, and then you can try some single displacement reactions on your own. Here's an example where I've got magnesium reacting with water, and I really encourage you to write the water as HOH. And think of it as a hydrogen ion and a hydroxide ion. It isn't really that. It's actually a molecule, but for the sake of predicting the correct products, just think of it like that. Magnesium is a metal. It's going to become a positive ion when it reacts. So if we look at this HOH again, we're going to think of the magnesium replacing the hydrogen ion in water. But again, that's only going to happen if it's more reactive or a more active metal than hydrogen is. If you look at our activity series, we're going to look for magnesium and we're going to look for hydrogen, and magnesium is more reactive than hydrogen, so we're okay to carry on with this reaction. So when we predict this product, what we're going to do is we're going to write the hydrogen by itself, and because it's diatomic, it gets a 2 beside it, and the magnesium is going to become an ion, and as an ion it has a +2 charge, and it's going to react with the hydroxide or combine with it, which has a -1 charge. So that's your first step. Your second step is to actually write the correct formula for magnesium hydroxide and then just balance the equation. So we've got Mg and then in parentheses OH taken twice. And then you just want to make sure that the whole equation is balanced. So when you balance it, it looks like you're going to need a 2 in front of this HOH, and everything's going to balance. Okay, I want to take you through this next example. In the next example, we've got bromine, which is a non-metal, and we want to see if it will react with ammonium iodide, which is NH4 plus I minus. So here, the bromine is going to replace the iodine because iodine is the nonmetal in that particular compound. And bromine's higher than iodine on the periodic table, so it's going to be more reactive. So what we do is we put the iodine by itself, and it's diatomic, so it gets a 2. And the bromine combines with the ammonium, but it's important to remember that ammonium is the positive ion, so it's going to go first. It's +1, and bromine has a charge of -1 as an ion, so it gets a charge of -1. So when you write the whole formula for this thing, it's going to be I2 plus NH4Br, and you're not going to need any extra subscripts or anything like that. And when you balance the equation, you're going to need a 2 in front of the 2NH4I and a 2 in front of the NH4Br, and it balances. So that's how you carry out a single displacement reaction. Every once in a while you might get a case where the element that's by itself is actually less reactive than the thing you're trying to replace, and if that's the case, you just say no reaction and nothing happens. This would actually be a good time to go and try your single displacement reactions before you listen to me talk about double displacement. But if you're here already, I want to talk about double displacement. I think double displacement in some ways is actually a little easier than single displacement, because in double displacement you're always going to be switching the front 2 ions. The 2 metals are just going to switch places. So here you see K with Cl, and then as a product the K is with the NO3. Here again I've got potassium and barium switching places. So the barium is going to go with the chromate, and the potassium is going to go with the NO3. It doesn't make any difference what order you write your products in. The thing that you're going to be looking for here is you're going to know you have a successful reaction if you make a solid, if you make a compound that's not actually soluble in solution, or something that will precipitate out of water. So I'm going to show you how to use a solubility table. Let's go ahead and I'm going to work through the first question here. A. Here I've got sodium chloride and calcium bromide. Just take the first 2 ions, the sodium and the calcium, and they're just going to switch places. So I'll write calcium, and remember that's a +2 ion, and that's going to go together with the Cl, which is a -1 ion, and that's going to react with the sodium is +1 as an ion. It's going to get together with Br, which is -1. So knowing all those charges, I'm going to correct my formulas. So CaCl has to actually be CaCl2. So that's a neutral ionic compound, and sodium bromide's just fine. The next thing I want to do is go ahead and check to see if either of these 2 compounds that I made are insoluble in water. Do they actually precipitate out? So this is where you're going to have to flip the page to page 21. This is a solubility table, and what you're looking for here, I'll just give you an example by looking up calcium chloride. We're going to look at our positive ions down here in this column, and our negative ions go across. So if I look up calcium and I go over here to chloride, looks like it's right here. Where they cross, the calcium and the chloride cross, I have calcium chloride as a compound, and the AQ, here's a little key up here, is telling me that I have a soluble or aqueous solution. That means it doesn't make a precipitate. If I want a precipitate, I'm looking for something that's either an I or an SS. I means insoluble and SS means slightly soluble. My picture here doesn't actually have, I can't see far down enough to see the sodium bromide, but I think you'll see if you take the time to look that sodium bromide is also aqueous. So that means that when we did this double displacement reaction, we don't actually successfully get a precipitate. So technically we have no reaction. So here we don't even really have to balance our equation. We just say, you know what, this is aqueous, and this is aqueous. And so we just say, actually, that's a no reaction right there. Let me show you one more example. So in this next example, I just take, again, the first 2 ions, lead and potassium, and I'm going to put them together and switch places. So the potassium has a charge of +1, and it's going to be combining with the NO3. Notice I'm just focusing on the ions as they come together. I'm not bringing over any extra subscripts, so don't bring this 2 over. Okay, and then lead, which is Pb, is going to combine with the iodine. Now I happen to know iodine's -1. When I look up lead, I'm going to notice it has a couple different possibilities for charges. It's going to keep whatever charge it had in lead nitrate. And over here, it must have had a charge of +2. So I'm going to keep this as Pb +2. So then I'm going to fix my formulas. Since K is +1 and NO3 is -1, that formula is fine. PBI must actually be PBI2. Then I'm going to have to go over to my solubility table and actually check out on the solubilities of these two things. Here I'm at the solubility table. I just looked up potassium nitrate and it was aqueous, so that doesn't help much. But here's lead 2 and here's iodide. And where they meet, I've got slightly soluble. So that's good. That means I've got an actual solid there. So this reaction is a go. What that means is when I write out this equation, I can go ahead and predict my products, KNO3 plus, and you can put a little aqueous next to that since we know that that one dissolves in water, plus PBI2, and you want to put a little S beside that. And then we're going to go ahead and balance the equation. I'm going to need 2 NO3s on my product side. Now I'm going to need a couple of Ks. And I think it balances. So again, the goal with double displacement is you really have to make sure you determine if a precipitate forms. If you're looking at single displacement reactions, you have to make a couple of different decisions. For single displacement reactions, first of all, you have to decide if your element that's by itself is a metal or a non-metal, so you have to decide what kind of thing it's going to switch with. And then you have to decide if it's actually reactive enough to make that switch. So that's where you're going to have to use the activity series if it's a metal, or you're going to have to look at those halogens and figure out if the halogen that's by itself is more reactive. So I want you to try the problems on page 20, and we'll definitely go over them in class tomorrow. And we'll be doing a lot of practice with this, but do your best, and we'll talk about it when I get back. See ya.
Made with Doodlecast Pro.